Okay, so my talk is about early afterglows. And the better title of my talk is possibly observational constraint on the magnetization of gamma ray burst fireballs. Okay. And okay, this is my talk outline. I briefly speak about gamma ray burst and the related emission process, components, and relativistic motion is essential ingredient in the standard model, and I remind you why it's important. And I will discuss how to estimate magnetization of GLB fireballs. Okay. And gamma ray burst is literally burst of gamma rays and rather soft gamma rays, and coming from random direction. And if you have whole sky coverage, we expect few events per day. And the light curve is very highly variable, and in some case, time structure could be as narrow as millisecond, and it indicates source size is very compact, let's say less than 300 kilometers. And the standard model, it's called fireball model, consists of 3 steps, and relativistic outflows, that main topics of this program, is ejected from compact source. And the compact source might be death of massive stars or compact stellar mergers, I mean neutron star, or neutron star black holes. And this relativistic outflow create shock at large radius, and electrons accelerated in shocks. And electron emit photons via synchrotron or inverse Compton process. That's the basic idea of the standard model. And this is more specific model. Let's say collapsar model, especially for long bursts. Today people believe that long bursts are associated with death of massive star. And at the end of their life, the core collapses into black hole, and the stellar envelope agrees into black hole, and it powers the relativistic jet, and this jet causes shocks, and accelerated electrons emit photons. And let's say there are 2 main emission components in GLBs. One is prompt gamma rays. Usually if we say gamma ray burst, maybe just imagine just gamma ray emission. And light curve is highly variable, and it could last maybe few 10 seconds, few 100 seconds. And the other main component, it discovered rather recently, but already more than 10 years ago. It's low energy counterpart. It's if you see in the same direction with lower frequency coverage, X-ray optical linear, we are going to see long-lasting component. And light curve is very smooth and described by Powell. So here it's gamma ray burst itself, and this is log-log. And in this case, optical light curve described by Powell. So compared to gamma ray itself, very smooth. And this component could last, if we use very large telescope, we can follow afterglow almost a year. Okay. So this is more standard, let's say more future included. From some argument related to variability, I say gamma ray burst light curve is very highly variable, and we can show that its burst wave cannot produce this kind of gamma ray burst variability. So today, people believe that compact central engine emit relativistic outflow, and during propagation, due to inhomogeneity inside the jet itself, shock happened, and it produced gamma rays. And this flow further expand into ambient medium, and it hitting into ambient medium and cause burst wave. And afterglow is coming from this burst wave, and gamma ray burst is coming from somewhat different dissipation process. And still this portion is a bit shaky, but let's say internal shock is standard model. And I might emphasize that basically afterglow, emitter is shocked ambient, and the internal shock is happening inside the jet itself. So emitter is original ejector from central engine. So there is energy transfer somewhere here, around 10 to 15, 16, 17 centimeter. Energy is transferred from original ejector to ambient medium. And especially if we like to interested in magnetization of original outflow, observation of usual afterglow doesn't tell us much about it. So we need observation related to emission related with original ejector. So I will discuss further later.
There is also reverse shock in the afterglow.
Yes.
So which is if the
yes,
afterglow
that's the next portion. That's the next portion.
Then it's the ejector. Right?
Yes. So this is almost same kind of diagram, expressing same phenomena in different with different variables. Here, x-axis is shock radius, distance from central engine, and the y-axis is the Lorentz factor of outflow. And initially, central engine is very compact, and in a very compact region, large amount of energy is injected, and it's very hot due to internal pressure, almost it explodes. And internal energy converted to kinetic energy, and it's going to accelerate rapidly. When internal energy is almost converted to kinetic energy, it's going to coast. And at the beginning, ambient medium is low density, so existence is almost negligible at the beginning. But of course, if this fiber expand up to really large radius, this existence of ambient become important. Basically, fiber is going to decelerate. And so here, deceleration happening. And at this stage, energy is transferred from original fireball to ambient medium, and later this phase is described by burst wave. And most energy in system is carried by burst wave. It is shocked ambient medium. So afterglow is coming from this burst wave. And here I discussed rather homogeneous fireball, but if we consider inhomogeneous fireball, or a more simplified picture could be if you consider multiple explosions, gamma ray burst, internal shock happens around this phase. Okay. And about this deceleration, this deceleration is done by two kinds of shocks, and one shock is propagate into ambient medium and accelerate ambient. And the other shock is, it's called reverse shock. It's propagate inside ejector itself, and ejector decelerates. And around shock crossing time, we can show that these two shock regions carry comparable energy. However, this ejector has much larger mass. So it means that energy per particle is much smaller in this region, so much lower temperature. So it means that if this region is emitting X-ray, we can show that this region emitting in optical.
It depends on the magnetic fields there.
Yes, depend on parameters, but let's say with the typical parameters.
You have zero magnetic field in the interstellar
Okay, so
medium,
it's coming to the point. It's coming to the point. Actually, that's the point. Yes.
But if, you're making a strong statement.
Yes, but okay, I'm going to discuss this portion later. Yeah.
Before you go any further, why it is so clear that if you have lower energy per particle, it will emit at lower frequencies?
Yeah, this is what I said, that you have extremely strong magnetic field, different magnetic field.
But
So-
you will even have different emission mechanisms.
Yeah. It's a. I say this is very simplified picture, and I'm coming to slightly more detailed discussion. Just later. And okay, so initially we considered like this simplified picture, and successfully we can understood like this phenomena. And during gamma ray burst, this telescope, almost the usual camera telescope, detected very bright optical emission, and the event itself happened at the redshift 1.6, but still optical emission is 9th magnitude. It's pretty bright. And as we expected, this component decay faster than usual afterglow brass wave emission. And this is first detection of optical flash, it's called. And we can really understood well this phenomena in the standard framework. And so, as already mentioned, there is another component concerning the emission from ejector. So if you consider this prompt gamma rays and optical flash might come from original ejector. And afterglow is coming from ambient medium. So if you like to study the property of original ejector, we need some information from these guys. And if we observe only afterglow, it doesn't help much.
Can I ask, how long should be the reverse shock? How long it lasts?
It's very short, and I mean a few hundred seconds.
Yes. Is it true?
It's of course it's parallel, and it depends on relative amplitude between forward shock component and the reverse shock component. And in this case, so let's say this peak time is typically a few hundred seconds.
No, I'm not talking about observations, because this is your interpretation that this optical flash is the reverse shock.
Yeah.
I'm just talking about the theory. If you just have the outflow, how long the reverse shock would last? How long it should last?
What do you mean by last?
I mean the observed emission from the reverse shock.
So it depends on situation. Example, if we don't have this guy at all, in principle, this can last really long.
Okay.
Just decay in parallel.
So you also expect a decay in power law from reverse shock
Yes.
too.
Yes. So okay, so this portion is just due to adiabatic expansion of ejector, shocked ejector, and just temperature going to drop. So due to that, emission decay. And for the shock case, Lorentz factor is a sweeping larger and larger amount of material, and Lorentz factor itself becoming smaller. But on the other hand, brass wave sweeping larger and larger amount of materials, it means the number of emitting electrons increase. So we expect this guy is decay shallower compared to this, because this guy is short-lived. It means this ejector is actually not the usual AGN jet, very thin shell structure. Let's say this wise could be comparable to source size. So once this guy cross shell, no new electron accelerate anymore. After that, just adiabatic expansion, adiabatic cooling. And so we expect emission from this guy decay faster. And applying the standard model, we expect to decay index about 2.
This assumes you have an instantaneous energy injection and not a continuous. And if you have a longer duration.
No, no, it's for reverse shock. Already newly accelerated electron just stop. Just
But I
once
mean-
heated.
Oh, yeah.
But the ejector is fine. It's not thin. It's 100 light
Yeah, yeah,
seconds.
this
Let's
guy.
say it's the duration of the gamma reverse, right?
So this guy is keep propagating
the ejector
and
itself
accelerate
is thick.
continuously.
If the gamma reverse is 100 seconds, the ejector has to be at least 100 seconds, light
Yeah.
seconds thick, right?
Yeah. Okay. And okay, what's the discussion point? Yes, okay. So we have let's say 3 components, and if we like to study about ejector, we need to observe this and this. This or this. And usually early afterglow means right after prompt emission, let's say few hundred seconds. And most robotic telescope targeting this emission. Robotic telescope mean these days large number of ground telescope is really automated. Once satellite is triggered by some event, the coordinate is automatically transferred to ground telescope, and automatically telescope pointing to the direction and start observation. And the example we are operating 3 2-meter telescopes, and one is in Spain, La Palma, and one is Hawaii, and the other one is in Australia. And usually we can start observation about 200 seconds after gamma burst. So to do like this observation, we need automated system. Otherwise, if somebody needs to stay all night, wake up all night, it's pretty tough. Okay. And essential element in the standard model is relativistic motion. Usually, we assume Lorentz factor more than 100. And like this, high Lorentz factor was introduced as a long time ago to overcome, it's called compact problem. The problem is following. We know that source is compact. It's inferred from variability timescale. And in compact source, huge amount of energy injected, let's say 10 to 51, 52 X. And it means we expect very optically thick source. On the other hand, observational spectrum is non-thermal and extended to very high energy, more than electron mass. So it's clearly somewhat contradict. And to overcome this problem, we introduce high Lorentz factor. So with this high Lorentz factor, larger source volume is allowed, and less photons at high energy in co-moving line. So due to these 2 effects, we can solve this problem. And other observational evidence support for relativistic motion is, okay, mostly, let's say, optical depth argument from high energy photons, basically the same. And recently, Fermi collaboration estimated for 10 GB photons to be optically thin, Lorentz factor even 1,000 needed. And other thing is onset of afterglow, maybe related to your question. And from very simple calculation, we can estimate when fiber going to decelerate. And at the deceleration time, it corresponds reverse shock crossing time. So we expect afterglow going to peak at the deceleration time. And from simple calculation, Lorentz factor and peak time can be related. And we need some estimate about explosion energy and ambient medium, but dependence is rather small, that's one is. So And usually, or typically, afterglow peaks around a few hundred seconds. So putting a few hundred seconds and typical numbers, we get the Lorentz factor a few hundred. So it's somewhat consistent.
How is that changed if you have a wind?
Okay, so scaling could be changed. Scaling index is going to change, but number itself was somewhat similar.
Sorry?
Number itself is somewhat similar. A few hundred still.
Yes, that does depend on the wind.
Yeah, okay, so let's say typical wind normalization. It depends on mass loss rate and the velocity of wind, but assuming typical number. And the other thing, example, radio afterglow. And one evidence is quenching of scintillation for this event 4 weeks after scintillation quenched. And it's indicating at 4 weeks after GLB, this size is about 17 centimeter. So it should be expansion speed should be close to the speed of light. And the more direct one could be done for rather bright near event. And people resolve radio afterglow image and expanded image resolved at 25 and 83 days after GLB. And this expansion speed should be 3 or 4 times larger than speed of light. This is superluminal motion. Of course, this expansion velocity is apparent velocity, and nothing can propagate more than speed of light. But this is apparent apparent velocity, and it's indicating source is expanding with almost speed of light. Okay. So we need really high Lorentz factor to explain gamma ray burst phenomena. And jet need to have really high Lorentz factor with high energy. And this is really long-standing problem, not only in GLB, possibly even in AGM science also. How to accelerate jet is pretty tough question. And these days, many people interested in Poynting flux dominate jet model. And part of the reason is now, I guess, large number of AGN people believe that AGN jet including magnetic fields. And so with Poynting flux dominated jet, maybe it's easier to achieve high Lorentz factor and collimation. Still, the physics is not well understood, but somewhat this kind of model is very attractive. So my talk is about how to test or investigate magnetization of GLB jet. Okay, so I will discuss about 3 methods. One is afterglow modeling and SSE component and polarization. Okay, and come back to this diagram again. And the point is first shock region. This is a shock ambient medium. And here, reverse shock is propagating into ejector itself. So emitter is original ejector. So if this guy is somewhat magnetized, magnetization may be different here and here. And comparing emission property from first shock and reverse shock emission, we might be able to estimate about magnetization in this region. That's the basic idea. And we have developed such a estimation method by using peak flux and peak time of reverse shock component and quad shock component. Example, this black one supposed to pack quad shock component. So this is light curve, x-axis is time, and the y-axis is flux. So at earlier time in optical band, we expect reverse shock going to dominate. So we have rather bright reverse shock component. Maybe it might separate two peaks. Maybe this guy going to be something like flattening. And so we can develop slowly how to estimate from this peak time and peak flux, how we can estimate the ratio of magnetic energy density in two shock regions. And so we have applied this method to few events, and this is one example. And this is optical light curve, and y-x-axis is time, and y-axis is magnitude. And at early time, optical light curve decaying rapidly, and around this case, 1,000 seconds after gamma ray burst, it flattened. And doing detailed modeling of this event, we get something like this number. Magnetic energy density ratio between forward shock and reverse shock is about a few tens. And so reverse shock regions seem to have a higher magnetic energy density, few tens times. But it doesn't mean pointing flux dominated jet, because for this event, we don't have information about actually how much is this guy. But typically, for other afterglows, typically epsilon b, it means magnetic energy density expressed as a fraction of equipartition value, which means shock energy. It's 10 to minus 4, 10 to minus 2. This is just typical number. So combining these two guys, still, even I say magnetized, but still most energy should be carried by baryons in this case also. And we have like similar number for these guys. So we might say we have some evidence of magnetized fireball, but it doesn't mean pointing flux dominated. But existence of reverse shock is not still well understood. I should come to the point. And the fireball model predict very bright early optical emission from reverse shocks. But large fraction of GLBs do not show prompt optical emission. And the reason is not well understood. So example, these are different events. And maybe this guy have somewhat steeper component at earlier time. This guy also, but most of the case, it's not clear. There is a distinct additional component or not. And more extreme case, this guy is, this is almost end of gamma ray burst, and up to 10 days, several days, X and optical light curve is discovered by just single power. And no indication about reverse shock here. So it's still, we don't understand yet. And there are few scenarios how to explain this. Is maybe reverse shock may be emitted at much lower frequency, or emitted at much higher frequency via inverse quantum process. or simply maybe due to dust extinction in host galaxies, because reverse shock happen at somewhat smaller radius compared to afterglow. Maybe dust effect may be larger. And maybe more interesting scenario could be if ejector is highly magnetized, maybe magnetic pressure suppress reverse shock itself. In that case, we don't expect any emission. But in some case, we have very bright optical emission. So it means in that direction of discussion, it means each ejector might have somewhat different magnetization. Okay. And about this scenario, maybe reverse shock is emitting photons at larger frequency. I did a slightly more detailed discussion, and especially in the context of, it's called X-ray flares. X-ray flares are one of the major discovery by Swift satellite, and it's a flaring activity in early X-ray afterglows. And this is the example here. It's a farther shock emission, expected farther shock emission, and we have flare here. This case is about 1,000 seconds after gamma burst. This case also, a few thousand after, or even 10 to 5 seconds after. And in some case, this flaring event is very drastic. This flux increase, this case, factor of 500, very significant. So interesting possibility, maybe this might be due to reverse shock. And if first inverse Compton is in X-ray, still second inverse Compton is not suppressed by climbing thinner, and second inverse Compton expected around 10-100 MeV. And we did somewhat detailed discussion, and at the end we found like this SSC model doesn't work to explain X-ray flares, and there are a few reasons. Example, to explain very bright flares, we need very extreme Compton parameter, and with this kind of parameter, we expect SSC emission coming to much above X-ray band. And other argument could be X-ray flare time structure is too sharp, too narrow to explain in the context of reverse shock. Reverse shock also kind of external shock. So it's very difficult to explain, very narrow feature. And reverse shock is just one shot. So obviously we have multiple flares. It's very difficult to explain. And the recent thing could be Fermi. I don't know how is the report, most recent result, but at least don't indicate anything about additional component around 10, 100 MeV. Maybe there is some secret, but and so today, standard model to explain X-ray flares is late internal shocks.
Why do you consider synchrotron of Compton? Why not just synchrotron? Because if in the reverse shock you should have stronger magnetic field, so it should be probably synchrotron should be already in X-rays, no?
But still factor of 20 concerning epsilon B.
Yeah, this is just your assumption.
Yes, yes. But if you assume same parameter scaling, typical frequency scale as just square root of epsilon B, and it's not going to increase much.
Yeah, but I mean, The magnetic field in the interstellar medium is microgauss. Magnetic field in the ejector could be, I don't know, many gauss. So it's this could be order of magnitude difference. No?
So you mean, okay, let's see. So you're assuming very highly magnetized
I mean, it's
ejector, and you
sufficiently
say arguing
magnetized.
Even synchrotron emission also coming to X-ray band, you say.
Yeah, why not?
Okay, maybe possible. I mean, didn't discuss the detail.
But are there any arguments against that? That's
Yeah, but on the other hand, okay, these are still against this kind of model, because reverse shock is one shot. We expect just one peak.
but you have inhomogeneous outflow, so why it should be one peak?
But still, it's difficult to explain really complicated variable flares. Just same argument, because the external shock cannot explain prompt emission. Exactly same argument we're going to apply. And okay, so still, if you're interested, you can
Yeah,
explore
we can
that
do-
direction. Yes, I didn't study in that direction detail.
Sorry, sure. About what you said before about the possible argument to explain the fact that you don't see optical flash in all gamma bursts, you
Mhm.
see a fraction, a small fraction. You said about the dust extinction.
Mhm.
Isn't that excluded from the fact that you see many bursts, bright optical, let's say, standard after emission that you can think coming from the foreshore? I mean, I didn't.
Yes, okay, so, yeah, okay, but the reverse shock emission region is slightly inside of,
I mean, the dust is inside.
I don't know, it's intuitively maybe dust density could be higher, closer to source.
The dust should be completely destroyed by the radiation.
I don't know.
I think there were several papers on that.
Yeah, I know some papers, but in reality, but in few cases, people arguing dust extinction actually in optical afterglow.
To suppress the,
Yeah.
the,
Yeah,
the optical flash.
I mean optical afterglow itself.
And
Yeah.
you shouldn't see any optical after.
But that point is not so clear, really.
Okay.
Yeah, just speculation. Still, we don't understand quite what is main reason for the lack of optical flash. Okay. So this is famous Fermi result, and here 10 to 1 kb to 10 to about 77 kb, almost described by single power in this case. And okay, SSC emission component argument can be discussed in the prompt emission also. In principle, we detect synchrotron emission, and in SSC component from internal shock, we can discuss magnetization. But there is no additional component here, just single power. And
Just curious, what was the spectral index of this power?
how much it was, Felix?
The spectral index of this power?
2.2.
Something.
The photon.
Minus 2.2.
2.
Yeah, just standard. Yeah, consigned to F nu 1.2. So there no SSC component mean magnetized dipole. One possibility. If a Compton parameter is small, we don't expect SSC emission. Or, of course, there is other possibilities. Maybe one could be SSC peak could be located much higher frequency. And okay, somewhat different thing. It's Fermi doesn't detect much high energy photons, and maybe actually source may be optically thick for high energy photons because, example, this case, rather large Lorentz factor is inferred, and from other observations, usually Lorentz factor is just few hundred. So to detect really high energy photon, maybe rather high Lorentz factor flow needed. So most of the case, maybe flow may be slower. That case, maybe we don't see much high energy photons. That may be one option. Okay. Okay, so, and about last portion of my talk is about polarization. And linear polarization is one signature of synchrotron emission, and once polarization is detected, it's somewhat indicating, in some sense, supporting synchrotron emission. And of course, to produce high signal, we need large-scale magnetic field. Otherwise, if magnetic field is really tangled, and if we see superposition of many polarization signals, it's going to cancel out. So we need a rather large magnetic field structure.
Excuse me? But if the magnetic field is tangled but it's just compressed by the shock, you still see some polarization.
Yes, I'm
That
coming
is why
to, yes, I explained
So you
it a
don't
bit.
need large scale magnetic.
But okay, but in random case, we expect polarization signal appear rather short period. Okay, I'll come to the point here. So, in the context of magnetized outflow, polarization measurement on prompt emission or optical flash are interested. And several years ago, once high polarization measurement was reported, but it's highly controversial, and today nobody is assuming it, and nobody believes it. But until quite recent, all polarization measurements are done at a later time, more than, let's say, half day after GRB event. But in the context of jet break, it is still interesting. Let's begin to discuss about it. But okay, maybe I should discuss about point. Okay, this is a thing. So if emission region has a large-scale magnetic field, obviously we expect a large polarization signal. And the other possibility is even if emission region has very tangled random magnetic field, still it's possible to produce high polarization signal. So it happens when line of sight just run along the edge of jet cone. And like this geometrical configuration happens at, it's called jet break time. Okay, so example like this. And so this supposed to shock front, let's say. And maybe magnetic field strengths may be different, parallel component and perpendicular component. Maybe magnetic field is produced by some kind of instability associated with shock. But that case, some guys arguing parallel component and perpendicular component have different strengths. So it means that if we see, so from edge, we might see some kind of alignment along shock front. And if this shock moving with relativistic velocity, due to relativistic aberration effect, this edge direction going to be almost propagation direction. So 90-degree in co-moving frame correspond to this gamma inverse angle in double plane. So if you see like this situation, we expect large polarization. Okay, so maybe I might discuss slightly further. So about jet brake, and standard model gamma reverse, it's called fireball model, both. But still, we can apply this spherical model to investigate jet, because as long as Lorentz factor of this expansion velocity is very high, due to the relativistic beaming effect, we can see only around line of sight about angular scale of gamma inverse. So observer cannot distinguish it's a spherical system or part of the sphere. But if this expansion velocity decelerates, we can see further larger and larger region around. If this guy coming to here, we are going to notice the difference. It's spherical, roughly maybe. And we notice emitting materiality is missing, and we expect decay become steeper. So this is, as a point, we expect polarized signal. And this is line of sight. And this is observable region, angular scale of gamma inverse. So if we see whole region, let's say this is polarization signal, just cancel out, and no polarization signal as net. But if this observable region is going to expand, so this is actual physical jet size opening angle. At some point, this observable region becomes larger, and part of emission region is missing. So emission region has asymmetry. That's why polarization is produced. That's one way. Okay. So in that, this kind of discussion was done rather long time ago, and people did polarization measurement around 1 day after event, and actually it's a rather low degree of polarization, but they detected polarization signal. And now about our telescope, our result, and our telescope is called Liverpool. And Linger is big. And so this is one of our telescope at La Palma. And on this telescope, we attached our polarimeter. It's called Linger. And polarization measurement is basically can be done if you rotate polarizer by 90 degrees and calculate the flux ratio. It is just in principle. But difficulty to measure afterglow polarization is afterglow luminosity changing very rapidly. So if you observe this way and rotate, during that, if intrinsic luminosity decrease 0.1 degree, 1 magnitude, this could produce false 5% polarization. So measurement is a bit tricky. And there should be few ways, but we applied rotating polarizer concept. Basically, polarizer is rotating with high velocity. And polarization signal is mapped around the circle. So like this. So this is gamma ray burst afterglow, actually beginning of afterglow, and polarization information is stored on this circle. And this polarization measurement was done just after 200 seconds after GLB. And this 200 seconds just correspond to the onset of afterglow. And theoretically it's very interesting because at the onset we expect at least 50% photon coming from reverse shock region. So, and unfortunately, but it was rather bright night. So we get 8% upper limit. So how we understand this 8% upper limit? So one possibility is we might argue if we have really large ordered magnetic field in emission region, we expect much higher polarization. So maybe let's say no large scale magnetic fields in the emitting region. But on the other hand, actually emission optical light curve is just like this, just one peak. And if we see two peaks, existence of reverse shock component is pretty clear. But even, okay, so if we can show that if typical frequency of pulse shock emission is below optical band, generally we expect just one peak, even if there is reverse shock component. But this is also fine. If reverse shock, in the reverse shock region, magnetic field pressure is very high, highly magnetized, and it might kill reverse shock. In that case, we don't detect any reverse shock emission. In that case, we don't expect any polarized signal. So still, two kinds of interpretation is possible for our observation. So we need more observations. Okay, so this is basically summary of my talk. So I discussed about how to test and investigate magnetized fireball model. And I discussed three methods. One is early afterglow modeling. And about, in principle, ratio between synchrotron component and SLC component. This ratio can tell us about magnetization of emitter. But so far we don't have very useful information. But the lack of SLC emission in Fermi may be explained or consistent with magnetized outflow. And I discussed about early polarization measurements. Okay, thank you very much.
Questions? Awesome.
This observation of the fluorescent was 200 seconds after the...
Yeah.
Can you push that quite a bit?
Earlier?
So much earlier and get better signal.
Yeah, okay, it's earlier it's better, but obviously it's very challenging. Yeah.
Sorry?
So,
Well, 200 seconds is that so challenging nowadays?
because before our observation, earliest observation was done few hours after gamma ray burst. And
I mean, even the VLT can do it in a minute or something like that, I think. And telescope like yours should be fast.
yeah, okay, if we're lucky, it might be possible to achieve earlier if we look into some direction and happen
Or would it be
nearby.
better to have a smaller telescope and, which can react faster?
Yes, ours are 2-meter telescope.
Mm.
And obviously, to detect polarization signal, we need very bright source and large telescope. It's detecting polarization signal is quite challenging comparing to just determining light curve. But yeah, if we're lucky, it may be possible to measure earlier.
When you you say that there are fewer optical flashes than you expect, do you mean that there are real upper limit on the brightness of the optical flash, or just there are no data?
Pardon, please again?
When you are saying that some optical flashes are missing, does it mean that there is no data?
There is. Example.
Upper limit, real one.
Yeah, okay. So example.
This afterglow is brighter.
Yeah, that's one possibility, but why it's brighter? That's okay. Not just one. This guy. So obviously we have data at earlier time.
So you do have data at right time, right frequency, but there is no signal. That's the point.
I'm not sure it's right frequency. It's supposed to emit at optical, but in reality maybe they emit at much lower frequency. That's one option.
And then when you discuss the model to fit magnetization, do you assume something about electron injection? I think you should. If you just assume magnetization parameter and that's it, I think you cannot draw the light curve.
So you mean?
You should assume something about electrons, about the electron spectrum.
So like this modeling thing.
You have shown a view graph with, yes, this one.
So assumption is here is okay. It's called epsilon e. It's a fractional energy to given to electrons. Same in reverse shock and first shock region. I took simplest assumption. In principle, maybe different.
But the Lorentz factors of electrons?
Electrons?
Yes, the injected electrons, they have same Lorentz factors or?
But typical electrons are different. Typical Lorentz factors are different because temperature is different.
Yes, but where it comes from? The Lorentz factor you assume in your calculations, where it comes from?
Okay, so in GRB community, what can I say? We don't know about first principle calculation, how to estimate how much energy is given to electrons and magnetic field.
Yes, okay.
So we took just phenomenological way, just assuming constant fraction of energy is given to magnetic field and electrons. So it's called epsilon b and epsilon e thing.
Okay, but then you have another parameter, the Lorentz factor of electrons.
And okay, so we assume random Lorentz electron distribution is power law.
Single power law?
Yeah.
There is gamma mean, there is gamma max. There are other parameters.
But P is about, okay, so index is about 2, and we don't need to introduce upper cutoff.
Okay. What about minimum?
Minimum is determined by typical energy.
What is typical?
It's less between ratio energy density divided by mass density. Basically, it gives you typical temperature.
Do you need to multiply by some Lorentz factor of flow of the shock?
No. Okay. So in co-moving frame, bulk motion it doesn't matter.
No, but if you have reverse shock.
Yeah, but it seems what you're saying is that you multiply by the Lorentz factor of the shock itself.
What sense?
Doesn't it make sense?
But relative Lorentz, okay, so random Lorentz factor is defined in co-moving frame, so bulk motion doesn't matter.
Yes. But
When you
that's
estimate
random
emission,
Lorentz factors?
surely bulk Lorentz factor is matter. But,
Yeah, I mean, okay. To reproduce the light curve, you want to know what is the frequency at which electrons radiate. To know the frequency, you should know the magnetic field, and you assume epsilon b. And you need to know the random Lorentz factor of electrons, which you also should assume somehow, I guess.
Yeah, so okay, about electron distribution, parameter is 2. One is power law distribution index, let's say about 2,
-2, okay.
and lower energy cutoff, and this give you typical frequency of emission.
Yes, but that's my question. What do you assume about this cutoff?
And this cutoff is determined by temperature of flow.
What's the temperature of the flow?
Energy density divided by mass density.
So it's basically scales like Lorentz factor of the shock itself.
In first shock case, or okay, general shock case, yes.
But if you assume some other sort of scaling, do you come to
But-
the same results or
But this might be rather reasonable assumption, and at least this kind of modeling is working well for wild shock modeling. Quite this kind of modeling successful to explain wild shock emission, light curve, spectrum.
When measuring depolarization, do you expect any effects of the external medium, some depolarization if you have a wind and a jet? So basically you observe your, like the source which is emitting synchrotron emission is behind some screen, right? And can cause depolarization or something?
Yeah, maybe if position degree is low, maybe it's not important. It's 1%. Position may be easily modified.
So you expect that these depolarization effects to be important or not? Like in general, just like for standard parameters.
But shouldn't modify largely. Or another possibility is actually in source itself. And actually we don't know how much fraction of electrons going to accelerate. And if small fraction of electrons accelerate to high energy, and if large fraction stay in thermal, this electron is going to maybe depolarize. You know. That is possibility.
There was recently also the claim on polarization signal from prompt of the gamma ray burst detected by IGRA. I have this. Did you see that? I don't
Yes.
remember what anything. I don't remember the name of the burst. But
But
do you think it's reliable, that measurement?
I'm not sure still. It's possibly yes. How many sigma detection?
I don't remember the numbers. I just have this in mind that it's maybe the first one is the one that you were claiming that was debated a lot. This one is the second one of the prompt. So at much earlier you were asking before if you can measure polarization. Yeah. So there are at least two. One is debated. The other one is very recent, 1 month.
Yeah, but the other confidence levels is rather low. I forgot numbers.
Okay.
And it's pretty tough to determine polarization in high energy band. So,
maybe about the optical polarization, that there is another problem. Actually, you can produce polarization just by dust absorption. If you have dust extinction, outgoing radiation can be polarized up to.
I don't know the
0.6%.
process well, so you know the process well?
That's for sure.
Okay, maybe we might discuss.
I mean, it can somehow hide the polarization. And I have no idea how you can.
That should be wavelength dependent.
Right.
Yeah.
Right, but synchrotron polarization also is wavelength dependent.
But the dust is
And also
one
water
is
supply.
the extinction process under to the -1.
So we
Yeah,
prob-
potentially,
we
yeah.
probably need,
This kind of.
That is something that
you need observations at different frequencies to distinguish the
Yeah,
frequencies.
yeah.
When you talk about monetization of the flow from the Fermi data, you say that we don't see the inverse Compton emission, but if your MEV emission is synchrotron, then you already have quite relativistic electrons, and the inverse Compton should be inclination regime. You
It's
probably don't-
maybe depend on Baruch Lorentz factor.
Yeah, but what's your Lorentz factor of the random factor of the electrons? The peak of the emission is already at MEV. So if your Lorentz factor of the bulk is few hundred and the Lorentz factor of the random factor of the electrons is thousands, then
Mhm.
it's still a klein machine.
Yeah, but okay, but let's see. But if you MeV and
Yeah, so
It-
you
it-
divide
it
by the
mean-
bulk, you multiply by the Lorentz
Yeah.
factor of the random, so you still get larger than 1.
yes, it depends on how much you assume. Yes.
Okay, any more questions? No more questions. Okay, thanks.
Yep. Thank
So,
you.
Thank you again.